All right. Thank you, everybody, for showing up. I'm going to start with just a few slides. I know most of you here came to hear Pradeep and how OCI is deploying their accelerated network architecture for AI factories. Oh, I got the remote here. All right, so you've seen some of those slides before. The adoption of AI in the enterprise is well beyond experimentation. It's now moving to production-grade, large-scale deployment. But what this data shows is more than just adoption of AI in production. It's showing the evolution of the very nature of AI. AI is no longer just acting as a chatbot, providing a simple response to a simple where, what, why. AI is no longer just reasoning before it's responding. AI is now executing multi-step workflows, going out and writing code, and actually functioning as an autonomous digital workforce, right? So this transition from just simple chatbots, simple conversational AI, to digital workforce is really driving the compute profile of the infrastructure served for AI. It's now transitioning to a large-scale sustained inference workload, putting strain on the infrastructure used for AI. Yes?
Take off your badge so it doesn't hit.
Oh, thank you. So you've seen this chart from Jensen. Jensen published his blog last week. It's showing the 5-layer cake for AI, all the way from taking raw energy and chips and translating that into industrial scale intelligence, right? Serving applications of all types. All software is using AI today or soon will be using AI today. So this architecture, this layered architecture, is also creating a virtuous cycle, a flywheel, if you like. The higher the performance of the AI factory used to deliver tokens, the most cost-effective token delivery is. The cost of tokens goes down dramatically. Just yesterday, in his keynote, Jensen showed the latest generation this year, Vera Rubin, delivering 10x lower token cost compared to just a year ago with GB300. The lowering of the cost of tokens, in turn, is driving additional demand, increasing productivity through applications using those tokens. And increased productivity allows for reinvestment in further improving and growing the scale of the AI factory to further improve the efficiency of token delivery and so on and so forth. So the AI factory model, right, becomes critical for sustained growth of AI infrastructure, of AI in our lives. Now, when it comes to operationalizing AI factories, there are 3 critical elements to that. It's about accelerating performance, right? The GPUs cannot be burdened with orchestration of the infrastructure. Stalling GPUs have direct impact on token delivery and the economics of token delivery. So infrastructure has to be tightly controlled to ensure best latency, best jitter, maximum bandwidth for AI factories to deliver maximum throughput. The second one is about efficiency and resiliency, right? Again, the GPU infrastructure should not be burdened with orchestration workloads like networking workloads, storage workloads, and security. There has to be a clear separation between the infrastructure workloads and AI factory GPUs delivering maximum tokens. And then lastly, and maybe most importantly in some cases, for the AI factory infrastructure to be cost effective, in many cases it has to be shared. has to be shared among multiple tenants. So from a security perspective, zero trust security is of course necessary, but no longer sufficient. There has to be a clear separation between multiple tenants sharing the infrastructure for the AI factory to deliver. Which brings us to the focus of this session, right? We came here to hear Pradeep because OCI is not only one of the most innovative CSPs in the world, they're also building the largest AI factories in the world, serving the largest model builders in the world. And they're delivering those AI factories all the way from power delivery, cooling, networking, and orchestration of millions of chips, all working in tandem. This orchestration term I use is what we refer to in some cases as the operating system of the data center, of the AI factory. And that AI factory is no longer the old school data center. It's not just used to store data or retrieve data from. It's an optimized infrastructure for the delivery of massive scale of tokens. One of the engines in delivering this operating system for the AI factory is our Bluefield DPU. The Bluefield DPU for us is the processor for supporting running the operating system of the AI factory. It's doing that by using our Docker libraries to provide access to acceleration engines in our hardware, allowing CSPs like OCI to not only offload their infrastructure workloads, but also accelerate the performance of their infrastructure workloads when they orchestrate the AI factory. Bluefield 4 also for the first time delivers what we call the Astra solution. Astra stands for Advanced Secure Trusted Resource Architecture. It's a mouthful. It was announced when we announced Bluefield 4 last year at GTC-DC. What it does is really allow, and it's now supported on all the NVIDIA Rubin generation systems. It's hardwired into the systems reference architecture. What it does is allow an operator to offload the entire control plane of the backend network of the AI factory into the DPU. So pieces of software that control either the congestion control mechanism, the multi-tenancy mechanisms, even the drivers of the network interfaces are no longer running on the host, potentially interrupting with tenant traffic. They're now completely offloaded to the DPU, which means we're finally delivering a true bare metal offering, starting with the Rubin generation NVIDIA systems. And lastly, of course, delivering zero trust security in a multi-tenant environment, meeting OCI's strictest security requirements. These are all delivered as part of the Bluefield DPU solution. And with that, I think it's a good segue for Pradeep to tell us more about the OCI Acceleron architecture.
Thank you, Caddy.
Thanks.
Good morning. All right, so let me first give a brief introduction about OCI itself. OCI started around 2016-17. That's when we launched, and we started off serving enterprise customers. But then the AI revolution came, and the model started writing poems. That's when we realized we are onto something else here. There's a very different trend. Obviously, clearly the models are not just for poems anymore. It's doing a lot more than that. Pretty much everything in our workspace, enterprise space, any type of information retrieval, information processing system is really moving to an agentic world. We have been seeing this, and we have been embracing this at OCI, and we've been serving many different types of AI customers over the last 3-4 years. Now, when we started OCI, we started with a thing called bare metal architecture, which is a Gen 2 architecture. But then, I'll talk a little bit about Gen 2, but the main key takeaway here is that AI is really changing that, changing the fundamental nature of it, where we really need to be thinking about AI-centric fabrics from a performance, from a latency perspective, from a reliability perspective, as well as from cost perspective. So from across the board, networking is becoming a very big part of the middle layer of Jensen's case. I really like the 5-layer cake analogy, so I'll use that. The middle layer is where we operate. We have GPUs, we have energy underneath, but how do we actually bring them together? That's essentially where the networking comes. And it actually plays a very important role in efficiently translating the energy and the GPUs into tokens, if you will. Now, it's, at the end of the day, the AI fabric revolution, if you will, is really first, driven by the scale of it. We are not talking about, tens of megawatts or hundreds of megawatts. We're really talking about, gigawatts or even tens of gigawatts. OCI, we have announced, many gigawatts of, data center size for GPU and other AI accelerators already announced, and we are on the way to building many of those. And that essentially presents a significant scale, right? And apart from that, you also have a very core set of requirements that is very native to AI itself. With AI, there's a huge incentive in bringing a lot of compute together in a very small amount of physical space so that we can network them together is extremely high bandwidth and very low latency. It is, you could actually take the hundreds of thousands of GPUs or even millions of GPUs and spread them across a very large geographic area. You would think it's the same energy and the GPU, but no, it's the networking really makes us pull everything together in a closed physical proximity so that we can network them together. And that brings in, data center energy level challenges and cooling challenges, but it also brings in, a new set of networking challenges. How do we actually, cluster all of them together in a very efficient fashion with low energy consumption so that pretty much all the energy can be given off to the GPUs, if you will, so that it can be converted into tokens. But at the same time, it has to be extremely reliable. Very, very reliable. And that reliability, actually drives, some of the big architectural trends in networking for AI as well. Now, on top of that, obviously security, particularly where, OCI and Oracle operate, enterprise customers care a lot about security, and multi-tenancy plays a big factor. Now, even if you think about a single large customer, enterprise customer, if you will, using OCI, we actually don't think about it, as a single customer. We sometimes view that as, hey, there could be different groups within that single customer, and they may have different types of workloads that need to be segregated and isolated and protected against. So fundamentally, multi-tenancy is not just about, corporate entities, it's about security domains. And that's where, the isolation primitives that are buried into the network architecture become very, very important. Just to give a sense for the scale, if you will, we were actually fortunate wherein we started working on at OCI, we started working on RDMA back in 2017 timeframe. And this was an Ethernet-based RDMA Rocky fabric, and we primarily used it. We never shipped it we didn't ship it as an external product to begin with. We used it internally behind Oracle Exadata service, if you will, which is our flagship database service. Behind the scenes, it used, Ethernet-based Rocky. Back in in 2017 timeframe, it was a very, very new, novel mechanism in terms of bringing a cluster network together. Now, since then we have built on top of that and come up with very large scale Ethernet-based cluster network technologies. We announced Zetascale last year. We announced Zetascale 10, which really spans clusters across a gigawatt campus, if you will. So the scale in the last 5 years from a cluster network size perspective has been tremendous. And on top of it, the GPU itself, or the AI accelerator, has the performance of it, both in terms of raw performance as well as performance with watt, has been increasing staggering proportions. So both of them bring together a lot of weight onto the network architecture for it to bear, right? And that's actually where Oracle Acceleron comes in. Now, Oracle Acceleron is a broad umbrella for a bunch of architectural changes, huge enhancements that we are starting to deploy at OCI. Fundamentally, there are 3 pillars to that. The first is host accelerators. The second is fabric architecture. The third is fabric accelerators. This is a combination of control systems and software that's written at microcode level all the way up to high level control systems, plus innovative hardware with partners such as NVIDIA, and where we use NVIDIA Bluefield chips, the latest generation chips, for implementing some of these extremely challenging security primitives while also not compromising on power or performance. And that is really the magic of this. The 3 pillars that I mentioned essentially boil down to 3 different product functionalities from a customer standpoint. The first is what I call as converged NIC. So going back, when we started off OCI, we looked at how virtualization is implemented in the cloud industry. The Gen 1 clouds essentially implemented virtualization using a hypervisor, if you will. The hypervisor essentially had some kind of driver, network driver, storage driver, and that essentially presented the virtualized devices to the virtual machines. Now, when we started off OCI, we took a fundamentally different approach. We took a Gen 2 approach where we actually took all the virtualization outside of the box. It's not in the server. And the only connectivity from the server itself to this virtualization is a very thin Ethernet wire. It's not thin physically. That's not what I mean. What I mean by that is the interface, if you will, is very thin from a security perspective. Now, when you think about a PCI interface, there's a lot of complex operations. There's memory, there's the bar, there's the various types of controls that can happen across a PCI bus. And the security threat vector across all of those interfaces is fairly large. Now, with a simple Ethernet cable, all that you can do is send Ethernet frames. That's it. Is very, very simple. And the simplicity of that interface is what provides a superior isolation primitive with the Gen 2 architecture. Now, when we launched OCI with this, and literally everything in OCI uses this, has always used it from back in the day in like 2017. Now, what is converged NIC? Now, you might actually think converged NIC sounds like, hey, it's another virtualization implementation on a NIC or something of the form, but it's actually not. What we did was we essentially took literally the same architecture that we had for Gen 2, which is essentially an off-box virtualization. And we asked the question, what if you go back to the previous diagram, there's a host NIC, which is part of the host. The customers can see it. As a virtual machine or bare metal compute instance, you can see the host NIC. And then there's an off-box virtualization device that customers don't see. All there is like Ethernet packets go through it. They don't even see. They just treat that as part of the network infrastructure, if you will. We asked the question, hey, these two are essentially connected using an Ethernet wire. And on both sides, they actually have expensive from a perspective of the ASIC footprint and power footprint perspective. They do have logic to convert a bunch of packet frames from the host NIC into an Ethernet frame, and that essentially requires a bunch of transformation. And then on the, off-box virtualization side, we again need to transfer them back to a place where we can actually store it in a memory and process them. We then ask the question, what if we can actually get all the security benefits of the off-box virtualization architecture, but not pay the penalty from a performance or power perspective? We essentially wanted to have a single chip, single hardware, where that Ethernet interface is still the same from an interface perspective, but it's a lot more efficient where it's actually it's inside the same hardware. And that's what converged NIC was all about. And we worked with NVIDIA on making some hardware changes to make this possible. That's really the secret sauce behind this, wherein we actually have a very hard isolated host NIC part of the hardware, and then a hard isolated off-box virtualization part of the hardware, and they're connected using a Ethernet like FIFO queue, if you will, right? So it's very simple. It's a hardware-based queue, but the simplicity of the interface, where it's just a bunch of Ethernet frames, is preserved, and that's really the crux of the converged NIC architecture. The second part of our Oracle Acceleron is essentially the fabric architecture itself. Now, the scale as well as the resiliency requirements driven by the AI fabric essentially forces us to look at very innovative ways to network the GPUs together. One of the things that we did was we looked at the network architecture. You typically have GPUs and you have a NIC. For 800 gig NIC or something of that form, and then it connects to some form of 2-tier or 3-tier Clo fabric, with or without oversubscription, whatever. That's typically the architecture that's deployed in most of the cluster networks. We then looked at it as like, hey, what if the NIC itself can act as a small first-tier switch? And turns out the NIC has capability. NIC actually has enough switching logic within it and has capabilities within it where it can actually connect to multiple switches at the next level. And that essentially, that change in the fundamental NIC capability from NVIDIA as well as from other vendors, it allowed us to rethink the network architecture in a fundamental fashion. And that's where we came up with multi-planar network. With multi-planar network, we are able to connect a lot more GPUs by taking network much broader than it would be for a particular amount of tiers of network. As an example, with multi-planar network, with a switch radix for a particular switch radix, which is a fundamental limitation of the switch ASIC itself, you can actually by just taking the network wider and wider, we can significantly scale up the network. And that scale is big. Now, we could do the same thing by increasing the number of tiers in the network, if you will. So if you look at in this fabric, there are 2 tiers in this fabric, but there are multiple planes. There are k number of planes. And that, the number of planes essentially becomes a scaling factor. Now, we could achieve a similar type of scaling by having a single fabric, but then adding more tiers. But turns out if you do the math, the cost, the power, and the reliability of it is all better with multi-planar network. One of my favorite aspects of multi-planar network is that with networking itself, if you look at a standard Clo network, it is, the architecture has a whole bunch of redundancy. A single switch or link repair in the interior of the network does not impact the customer significantly. So that is already part of the architecture. However, what we observe in practical terms when we operate large-scale cloud networks is that a bunch of failure modes are not related to a switch failure, but it's related to a control failure. Maybe it could be in the form of a BGP issue, or it could be in the form of, in OCI case, we have our own custom mechanism to signal routing and reachability, and it could be that's in the granularity of a fabric. And if there's a problem with the control element of it, affected, then the entire fabric is affected. With multiplanar, this really gives us isolation from a control perspective for each one of this plane. So what that means is that one plane fails, not just switches, but maybe even the control system in that plane fails, the network connectivity is still there because the other planes are working fine, right? So this is an incredible, this is very exciting change from my perspective. As a cloud operator, availability is a huge deal. And this is a very exciting change that multiplanar brings to us. I mentioned the large scale, and one of the things that we recently announced late last year is Zetascale 10, where we actually have 16 zettaflops of cluster compute. We are right now implementing this in one of the large gigawatt scale sites. This is essentially, you can think of this as, the previous year, 2 years back, we announced Zetascale cluster network, which is essentially, think of this as, one of these boxes, right? And then with Zetascale 10, what we are doing is we are taking a whole bunch of these clusters and then doing a master cluster across all of them so that they can actually act as if, it's a giant, cluster. So a customer can run a training job across the entire campus, not just building, not just one cluster network, but across the entire interconnected campus of GPUs. So it's really exciting, in terms of scale, in terms of what you can achieve from training perspective. Now the third big pillar of Acceleron is security. Now, obviously, the conversion NIC itself, brings to bear a very important security primitive in terms of isolation, right? While also not compromising on performance or power. Now, on top of it, we recently launched Zero Trust Packet Routing, Zipper, which is a very exciting new way to look at network security altogether that we are delivering as part of Acceleron. Now, I've been with networking for a long, long time. And firewall rules and ACLs, those are essentially being the fundamental building blocks of network security across the board. If you closely look at the firewall rules, it actually, or our routing rules, it actually does two things. It actually sets security policies, but it also sets up networking policies along with that. Because when you set firewall rules, you have IP CIDRs or ports or whatnot, and you essentially have rules based on that. So it's a combination of security rules and network rules combined together. So when you actually set, an enterprise sets firewall rules or of any form, there are two parties that actually have a say in it. And the two parties kind of need to sign on. There's a security admin, and then there's a network admin. Both need to make sure, the security admin can't just go put whatever firewall they want to secure the network, because that might fundamentally break the network in a surprising way. And the security person may not realize it. At the same time, the network admin can make arbitrary rule changes to routing rules or to the firewall rules, because that might actually change, break the security paradigm that the security admins are thinking about. So, fundamentally, the challenge here is that the implementation of the way, customers specify the firewall and the routing rules essentially combine the function of two very different entities that have very different mindset and goals in mind. Zipper essentially unties those two. With Zipper, you can come up with, policies, security policies that are independent of the network architecture itself. So with Zipper, we essentially have a bunch of resources that are tagged in a particular way, and Zipper policies essentially say, hey, these resources cannot talk to the internet. It doesn't matter if the routing rules or firewall rules allow it or disallow it. Zipper policy just enforces the security policy on top of the networking. So that really is very empowering for security admins, and they are able to enforce security policies without knowing that the network admins are not going to break them. All right, to sum it up, OCI, OCI Acceleron and OCI AI Fabric brings to bear a lot of new innovation in terms of scale, in terms of reliability, in terms of security. And it's all possible thanks to our hardware partners like NVIDIA, where we've been working very closely, hand in glove, to implement some of these really tough functionality in hardware. Thank you.
Thank you.
I'm going to hand it over
Very kind. Yeah, thank you, Pradeep. I'm going to try to wrap up really quickly because I want to leave time for some questions from the audience. So just to sum it up, Bluefield is the processor for the operating system of the AI factory, really powering growth in AI everywhere. It delivers performance with our accelerators and offload engines. It delivers efficiency in a complex multi-tenant AI factory, and it delivers the security capabilities required for operators like OCI deliver trust to their customers. That's it from me. John, are you going to help us with questions from the audience?
Thank you, Pradeep. Thank you, Gadi. I'd like to invite the audience to submit questions. We have a microphone up here and a microphone in back. Please raise your hand if you have a question for... Okay, we'll start right up here.
Yeah, thanks for a great presentation. My question is, as the workloads are shifting more and more towards inference, how do you think of clusters and cluster sizes? You gave a great example of a very large cluster for training. Do you have some, principles in terms of how a customer should think about clusters themselves, given the shift towards inference?
I can take that. So, from OCI perspective, we don't see a fundamental shift of that form. Now, I think, if you think about campus-wide cluster network, I think training is, primary goal of that. But if you think about, maybe a building level, 100,000 GPUs and whatnot, we actually see that as being a really efficient target for inference workloads as well. And the reason for that is inferencing is not like, a thing for, one GPU or half a GPU. Those days are with the, with the advent of agentic inferencing, if you will, the complexity behind the scenes for inferencing is significantly higher. That's one. Two, if you look at some of the complex agentic workflows, they're not single inference lookups. They're like lots and lots of inference lookups that need to happen. In the middle, they could be some other tool lookup, some other tool calculation, whatnot. But at the end of the day, in order to complete an end user request, or I don't know, let's call that a SaaS workflow request or something of that form, there's usually a lot of inference requests that need to talk to each other in some fashion or form. So we do see large clusters of AI accelerators as being a very compelling platform for foreseeable future.
Well, one wrinkle to what Pradeep described, I would add, specifically for the north-south interface on those GPU nodes, and Bluefield is used as the north-south interface, we do see that inference workloads drive new requirements in terms of the bandwidth requirements for this north-south interface. Especially as it goes to like an agentic model, inference workloads really driving large contexts, coding agents, those translate into more bandwidth on the north-south interface. This actually is what made up actually pulling our schedule for Bluefield 4 for OCI, come out with Bluefield 4 as an 800 gig interface on the north-south as part of the Vera Rubin platform.
Yeah, I would actually even expand on that. We do see, the core infrastructure requirements do, change as you go to inference itself in terms of the memory, in terms of compute requirement, in terms of, local storage requirements. But fundamentally, the cluster network concept is still the same. The size of the campus is still valid. So there's no problems there. But the exact hardware that we land, for inferencing sometimes needs to evolve along with that, along with, Bluefield north-south bandwidth.
I got it here. Yep. Hi, Pradeep. Thank you for inviting us. So I have a question related to host-based networking. You have rightly mentioned multi-tenancy is required. So once you are running your workloads on host, and host-based networking is on Bluefield, so it means there will be some performance overhead. Another way is you can do multi-tenancy by extending your network segment to your fabric, but that's a cumbersome approach. So have you done some performance benchmarking once you are running your workloads, overlay networking on Bluefield? It definitely you have to run multiple protocol stacks. So is there any performance benchmarking has been done on that?
Let me try to understand the question. You're asking, is there a performance bottleneck because of Bluefield?
So once you run your overlay networking stack on your Bluefield, so definitely you have to run multiple protocol stacks.
Yeah.
So does that add any performance overhead?
Yeah. So look, at the end of the day, if you take a packet and not do much with it and just pass it on, that's obviously the lowest, overhead, if you will. But the good thing is that, if you look at Bluefield architecture, it is designed to support the required virtualization without compromising on packets per second or throughput. So we are seeing, line rate throughput at, a reasonable packet size. So we don't view that as a performance, bottleneck per se. Now, obviously, it does have some, components that help with, the virtualization processing. There's power element to that, but that's all, within, it's a very, very small, relatively speaking. So fundamentally, we don't see that as a problem.
Thank you. I have two questions, one for NVIDIA and one for Oracle. Like for NVIDIA, you talked about backend offload with Bluefield. So for Vera Rubin, will it kind of go through Vera, or is there a direct point-to-point through which Bluefield talks to CX9? Like, how does that work out? Like, how is the config passed on, basically from RDMA NIC and the Bluefield NIC? That's broadly the question.
So Bluefield is used as a north-south interface of every Vera Rubin compute tray. That Vera Rubin compute tray separately also has east-west interfaces based on ConnectX-9. Those are the ones that are critical for performance with RDMA networking that Pradeep talked about.
Okay. Okay, for OCI, the question is, like this multiplanar system, is it like there are multiple ports going to multiple switches, and then there will be a failover mechanism, like there's a RDMA link flap, and because of which it just switches to a different port, and hence we maintain continuity in operation?
Yeah, so from an implementation, from an actually design standpoint, there are multiple ways one could do multiplanar. It could be multiple ports going to different planes, but it can also be a single port, single transceiver, but different lanes, branching out to, different ports, as long as, the port itself supports, that type of split, right? So going back 5-10 years, that wasn't quite the case, but now with the 800 gig NICs, you can actually take 100 or 200 lanes, separate them out, and take them to different planes.
Time for one more question. Okay.
Thank you. So I think to get the greatest benefit from all of the NVIDIA firmware upgrade, basically OCI has to do a lot of NIC upgrade as well. So how to do it at scale and really enforce we're getting the best reliability?
Sorry.
Could you repeat the last part of your question?
So mostly it's a question for OCI. So if we want to be able to do frequent firmware upgrade on NIC and ensure it's always available, what are some, I would say, best practices we're enforcing?
Oh, how does a customer do firmware updates? Yeah, so there are a few different models. I think with bare metal compute, we generally customers are responsible or essentially own the entire host, including the NIC itself. As part of the fundamental product model, we don't actually do the host NIC firmware update on our own, which is good because we don't interfere with customers' workload. So it's customers owns that part. We have mechanisms to provide that, and we essentially work with the customers. We have automated workflows where you can actually get the updates, and then customers can apply them. If you look at virtual machines based NICs, the virtual machines also support NIC. There, we actually own the operations of the NIC. We actually do the firmware update on our own. In many cases, they are invisible to customers. So we just do that behind the scenes so that they bump up to the latest firmware with the right security patches.